Hello, it's my great pleasure to present our work, Generating Pedagogically Meaningful Visuals for Math Problems, a new benchmark and analysis of text-to-image models. Let's imagine a student trying to solve the following math problem. At home, Marine made 10 cookies, which she will distribute equally among tiny jars. If each jar is to contain 3 cookies, how many cookies will remain unplaced? The student seems confused about the problem. Could you use visuals to help the student understand this problem better? The teacher might draw a figure like this on the blackboard and guide students through each part of it. For example, by asking questions such as why each jar contains 3 cookies or what the remainder represents. This process helps students better understand the problem. People may wonder, why should we use visuals in math education? As shown in this 3-step cognitive model, solving math problems involves text comprehension, solution planning, and execution. Primary school students often struggle with understanding the problem text and constructing a mental model that captures the underlying mathematical relationships. And here, visuals can help with grounding abstract mathematical concepts in concrete, familiar context, clarifying the underlying structure of a math problem, such as how quantities relate or which values depend on the others, and reducing cognitive load while supporting cognitive processing. However, creating these visuals is time-consuming and requires considerable effort. Besides, we are lacking of an established design space for visuals representing math problems. There's also no established generation framework for generating such visuals. In response to these challenges, we co-design a pedagogically meaningful visual design for math problems with primary school math teachers. After that, we develop Math2Visual, a framework for generating such visuals from math problem text descriptions. During the co-design phase, we conducted an exploratory study with 5 primary school math teachers experienced in using visuals to teach math problems. Each teacher participated in a 1.5 to 2-hour session, where we reviewed 6 visual design variations across 7 types of operations. Insights from these sessions inform the development of the final visual design. After the study, we finalized into 2 design variations, namely the formal and the intuitive. The formal visuals depict mathematical relationships in a symbolic style, help learners understand the underlying math relationships in a clear and mathematical way. The intuitive visuals represent the mathematical relationships in a context-rich, example-based way, improving engagement and reducing cognitive load of students. Here, we present the example intuitive design of different operations. For instance, in subtraction, we cross the object that has been subtracted. In unit transformation, we use a purple bubble to indicate the value after unit transformation for each object. To support the generation of the final visual design, we developed the Math2Visual generation framework, which enables controllable and accurate visual generation from math problem text descriptions. Suppose we have the math problem and optionally the corresponding solution. We feed them into a large language model. Using in-context learning, we generate a predefined syntax called visual language, in which we extract relationship and object we need to visualize from the math problem. The visual language is a hierarchical language with a structure closely resembling the expression tree of solution expression. It represents math problem using 3 core components: operation, container, and entity. We then feed the visual language into the renderer. The renderer first parses the visual language into a tree structure, then performs layout planning based on that structure. Finally, it draws the visuals and places the corresponding icons from the icon dataset. And finally, generates such visuals in SVG format. To evaluate our generation framework, we did 2 sets of evaluation. One focuses on the generation of visual language. The other focuses on the final visual generation. Here shows the results of evaluating visual language generation. The edit distance measures the edit time needed to convert the generated visual language into the ground truth visual language. The logic match ratio measures from all the generated visual languages how many of them matches the ground truth regarding operation and corresponding entity quantity. As shown in this table, our generation framework equipped with the O3 Mini achieves the best performance with logic match ratio around 97%. We also show that Llama model fine-tuned on the ground truth visual language dataset achieves comparable performance with state-of-the-art learning models. We further found that including the solution expression of math problem can significantly improve the quality of visual language generation regarding both criteria. For evaluating generated visuals, we need to first define the evaluation criteria. We reviewed relevant educational literature and consulted with primary school math teachers to identify this most suitable criteria for our task. This process resulted in 4 key criteria: accuracy, completeness, clarity, and cognitive load optimization. The completeness evaluates whether all elements necessary for solving the math problem are present in the visual. For example, the left side visual lacks a reminder part, which is incomplete for addressing this problem. The cognitive load optimization assesses whether the visual minimizes unnecessary cognitive load caused by the distractions or redundant details that do not contribute to the problem solving. For example, the left side visual contains too many unnecessary details that do not contribute to the problem solving. Here we show the result of evaluating visual generation. As shown in the result table, our master visual framework equipped with the best LLMs like O3 Mini and Gemini 2 Flash achieves the best performance across different criteria comparing with state-of-the-art text-to-image models in generating these visuals. We also show that fine-tuning learning model with our visual language dataset can achieve even better visual quality compared to advanced LLMs like O3 Mini. And fine-tuning text-to-image models on our generated dataset can improve the quality of visuals across all criteria. Finally, we found that including the solution expression of math problem can significantly improve the quality of visual generation regarding all criteria. Current state-of-the-art text-to-image models struggle to generate visuals from math problems. Here we present 4 example visuals generated by this model. The first one shows the wrong quantities that may confuse the student. The second one is missing important contextual cues that are actually needed to solve the problem. The third is really ambiguous. You can barely tell what it's trying to show. And the last one includes too many distracting details, which just adds to the cognitive load instead of helping. There are 3 key findings of this project. Firstly, Math2Visual can effectively generate pedagogically meaningful visuals from math problem text descriptions. Secondly, providing the LLMs with solution expressions leads to higher quality visuals. And last but not least, the proposed visual design and evaluation criteria can be used to guide the generation and evaluation of educational visuals in future work. Thank you so much for your attention. We have the paper and GitHub QR code here, and we are really looking forward to see you during the conference.